Okay, folks, let's finish chapter 11. At least, almost finished. I'm going to cover it out of order, which is hardly a surprise. Uh, and there's one piece that I'm actually going to leave for next week when we cover chapter 12, because I think it'll work better there. It's fine. Um, so yeah, let's let's finish the bulk of chapter 11 at any rate. And this part of the lecture will be driven primarily by slides that I'll post with this video. Although I'll toggle back to the whiteboard for a couple times just to kind of fill in the gaps that the slides leave. Okay, let's get started. So yeah, we've talked about oscillation so far, or another word for that might be vibration. And if we've got a medium, some sort of system, I guess, that extends away from the point where we are actually causing oscillation. In other words, if we've got some sort of surface, like a water in a basin, right, or some sort of sink, and we tap the surface of the water, we can cause ripples to propagate away from our, disturbance point. If we have a string, if we vibrate one end, if we cause one end to oscillate, we can get that disturbance to propagate along the string to the other side. The phenomenon that transfers disturbance or energy, the energy that we're adding by oscillating one side of the medium, that transfers that from one point in the medium to another point, let's call that wave. Let's call that a wave. This slide is talking about, actually, it's a picture of a pulse, a single wave pulse, just up and down, that's it, that it is initiated with vibration, with oscillation, motion up and down, and we can get that disturbance to propagate along the string. If we continued to oscillate the one end in simple harmonic motion, SHM, then we could get that oscillating disturbance to propagate along the medium, and we'd end up with a continuous wave. Okay, so we need to know how to describe a wave. There are, well, let's see. There are 5 things, really 4, but 5 characteristics that we need to be able to define about a wave to fully describe it. A few of them we've already talked about, amplitude, period, frequency, and there are 2 more that we need to introduce. We know that the period is the amount of time that it takes for one cycle of the oscillation to repeat, from equilibrium line up to past and back. How much time does that take? That's the period, okay? And then the frequency and the period are just reciprocals of each other. What if we had a disturbance propagating along this string, and we took a photograph of the shape of the string at some instant in time? We still have, we've got the top, the positive amplitude for our first initial disturbance, our first cycle. And that top, if we're going from left to right, that top is over here. We pulled the string up and then back down and then net further down and then back to equilibrium. And then we did it again and we're about to do it again. But that first crest, I guess we could call it, point of maximum amplitude positive displacement, is going to be followed by another point if this is simple harmonic motion without any damping, just, up and down, same amplitude all the time. Then there, some time later, we'll be making another maximum positive amplitude kind of displacement. And those two points along the string are going to be separated by some physical distance, because our first maximum amplitude will have traveled along the string some distance by the time we get to the next one. That distance, the distance between consecutive points with adjacent cycles, let's call that wavelength. It's like period, but it's not the temporal extent of one cycle. It's the spatial extent of one cycle. How much space does one crest propagate before the next crest occurs? Or if we look from trough to trough, or if we look from one point on that sort of wave to whatever the next corresponding point is. We'll use that symbol lambda, this thing, the upside down backwards letter Y. It's the Greek letter lambda, Lambda. Lambda. And then there's one more thing we need to talk about. The crest travels a distance in an amount of time equal to one period, because the wave is going to be able to travel so and so fast along this string. So we'd like to talk about how fast this disturbance from one side to the other can actually travel along the string. So I'm going to stop sharing the screen for just a second. I'll come back. If we're interested in speed, we need to know the distance traveled over the amount of time that it took to travel that. Now, if we're talking about one cycle, we know that it takes some amount of time, capital T, one period, to make one cycle of the oscillation. But we've just defined the distance traveled during one cycle is lambda, the wavelength. And division by period, that's like multiplication by frequency, because frequency is 1 over the period. So this formula on the slide that I'll go back to in a second, V equals lambda F, that's just our old kinematic definition for velocity. There we go. Okay. So those are the 5 things we need to fully describe a wave: amplitude, wavelength, period, frequency, speed, or velocity. Frequency and period are time domain. In other words, we need to know how much time is going by. We have to have a stopwatch and be able to track the motion as time goes on. Wavelength is a space thing. I don't need a stopwatch anymore. I need a ruler, and I need to see what the shape of it is at some instant so that I can measure the length between things. So we need a space picture for wavelength, and we need a time picture for frequency, period. Amplitude we can get from either one. It doesn't matter. We just need to know how much the how far from the rest horizontal is the maximum displacement of the points on the string. So we can measure the amplitude with either a space picture or a time picture, but we do need both to calculate the speed. We need to know how much space in how much time. That's velocity That's our formula. So we're going to need both in order to find that fifth piece, the wave speed. How many kinds of waves are there? And the answer is two-ish. Essentially, there are two, and it's the one we've already looked at, like waves on a string. We've got motion of the oscillation, and the individual particle of the string moves up and down, but the wave itself propagates perpendicular to that across the page. Think of this like the wave that you do at the stadium at the ball game. So everyone's in their seats, and then everybody stands up and then sits back down. All you're doing is standing up and sitting back down. Your individual motion is up and down, but the wave travels around the stadium, right? Perpendicular to your individual motion. So think of it like you are moving across, like transit or transportation, across the motion of the wave itself. So we'll call that transverse. Now, what if you were moving longitudinal, the same direction as the wave itself was going? And that's a little bit harder to imagine, but maybe I can try to demo it. Hold on. So I've got a slinky here. Let's see if we can get a good picture of this. Let me stop sharing the screen for a second so we can zoom in on that. We've got a slinky. And what I'm going to do is just let go of a little bit of it over here. And you can see that disturbance as this bit of the slinky pushes this way. That gets carried all the way down to my other hand. And then it'll bounce back and forth within that. But we're talking about sort of motion like this, back and forth along the same direction that those waves are traveling. Periods of compression of the medium and expansion. Instead of up and down, we're talking about squished together and then pulled apart, and then squished together and then pulled apart. As I cause my vocal cords to vibrate, they vibrate against the air inside my throat. And that air, those air molecules, are pushed against by my vocal cords. Those air molecules get kind of pushed out of the way and collide with the nearby air molecules. And that sort of chain of air molecules getting pushed together, and then the ones over here getting kind of knocked into the ones next door, and then those getting knocked into the ones next door. That period of that repetition of squished together and pushed apart and squished together and falling apart, that's motion along the direction of propagation, a longitudinal wave. So sound is a great example of a longitudinal wave. There's a third. I said there were two, and that's true. There's motion perpendicular to the direction of the wave speed, the direction we're actually going, the direction of propagation, and there's motion parallel to that. There's a third kind of wave, and that's the kind of wave that happens at a boundary between two media. We'll call that a surface wave. And we get this kind of, well, yeah, there's motion back and forth, longitudinal, but there's also motion up and down. So it's kind of transverse as well. So it's, all right, well, which is it? It's both. It's a surface wave. And I've got some demos of that we can look at. So we've got this surface wave propagating from left to right across the screen, and the actual motion of this little chunk of, I don't know, water right here, I guess, is in some kind of circular back and forth and up and down. It looked at in a slightly different way. Again, we have motion back and forth and up and down. So it's some kind of like combination of transverse and longitudinal. Um, that's another example if you'd like one. And you can see that this sort of disturbance is flowing throughout the medium. Let me go back. It's not only at the top, but that this kind of circular motion extends a little bit further down until we get to the, relatively deep in this medium, and the motion is almost entirely just sort of longitudinal. Let me stop that and go back to this. It's that down here close to the far away from the surface, the boundary between the two media, the motion is almost entirely longitudinal. Okay. If a wave is supposed to transfer energy from the source, the vibration that is the source of the wave, across the medium to someplace else, then we need to know how it does that. The energy transported by a wave is proportional to the square of the amplitude, which is true also of the energy in simple harmonic motion. We know that the total energy we have is related to the amplitude of the oscillation. That the total energy we have is related to the amplitude. Now, they've defined some stuff for us. We've got this new idea that intensity, capital I for intensity, which isn't moment of inertia, but which is intensity, is defined as power over area. So we've got energy propagating through space. What is the area over which we're spreading it? How much energy per time, because that's power. Energy per time divided by the area across which we're propagating, that's intensity. Now, I is proportional to amplitude squared because the energy is proportional to the amplitude squared. That A isn't area, and that confused me just right now as I was looking at it. I said proportional to A squared. No, it's inversely proportional to the area. Oh, right, because that's amplitude. So amplitude in these slides is A. Area, well, we don't have a variable for that yet. I just wrote it as area. So let's figure out what that variable ought to be. If we are spreading this disturbance three-dimensionally, like a sphere, then at each time we're watching one of these crests spreading outwards. The area that that crest is being spread over is the surface area of a sphere. And okay, the surface area of a sphere, surface area of sphere, 4 pi r squared. Which is why the slide says that the intensity is inversely proportional to 1 over r squared, because the area over which we are propagating, distributing the power that we've got, is that surface area of a sphere. So as we go farther away, the intensity that we are experiencing gets reduced by r squared. So if we double the distance, we reduce the intensity by a factor of 4 because we had to square the double. Okay, with all of those definitions, we can talk about exactly how the intensity is determined by all the different things going on. Let's take a look. And suddenly there's a whole alphabet here: pi, rho, s, v, t, f. Where's all this coming from? Okay. I'm gonna stop sharing the screen for a second so that we can take a look at the whiteboard. And let me grab my notes. Where did I put my notes? There we go. Okay. So, remember, let's think about, just for, let's think about this like a spring, like a slinky, right? That we've got some kind of medium and we're sending an oscillation through it. So we've got this sort of a little chunk of the medium that's moving, carrying the disturbance at any rate. So I'm just kind of imagine the formula we ended up with last week for the period of the oscillation of a mass on a spring. So the spring constant, c squared oh, wait a minute, hold on. Okay, so we square both sides, then we cross multiply by k. This was 4 pi squared. This is just m divided by t squared. But divided by the period squared is multiplied by the frequency, because the period is 1 over the frequency. So that's just times f squared. So this spring constant, we can rewrite it as that whole noise, 4 pi squared m f squared a squared. And that's where a lot of these letters come from. Okay. Now, let's see, we've got a factor of a half and a factor of 4, so that's going to get us a factor of 2. We've got our pi squared. The mass of the medium we're talking about. Now, let's see, where can I put this? Remember that the density of a thing is its mass over its volume, v, not velocity, volume. So the mass m is the density times the volume. Again, not velocity, volume. So this mass, we can write that as the density times the volume. And let me annotate this in a different color. This will be our signal that this expression is a replacement for the mass. F squared A squared. Now, the volume of that little section of stuff that we're propagating through, that little section of stuff has some area and some thickness. And remember that area times thickness, that gets us volume. So this 2 pi squared rho, this volume is area times width, if you like, some thickness, area times length. F squared A squared. Now, but it's as thick as it is because that's the distance we can travel in some amount of time, however much time it is, depending how fast we're going, right? So it's only because we looked at a little window of time, t, that the thing was actually able to travel through that length, L. So, wait, where did the thing go? The velocity should be the distance traveled over the time that it took to do that. So that length, gosh, this is getting kind of crazy. 2 pi squared rho. Oh wow. See, there's no chance to stop me when I do stuff like that. So I don't know. I wrote A, but I'm already using symbol A. So can I change that and use the letter S for surface area? Just so that we don't accidentally think that that should be A cubed, like I almost did. 2 pi rho S. When we have L, we can write VT F squared A squared. Okay. So that's the amount of energy that is propagated, transferred, transmitted by this wave through this area in this much time because it's traveling with this frequency and has this amplitude and it's traveling through the medium at this velocity. The medium is this dense. There's a lot of things going on here. Most of it we don't really need. We know that power is energy divided by time. I'm going to erase this stuff over here so it doesn't get in the way. Power so we take this whole expression for energy, divide by t, so we'll cancel the t, and we just have this whole noise, 2 pi rho S V F squared A squared. And the intensity is power divided by area. So we just found power, so we're going to divide by area, intensity, power divided by area. Remember it, see, not A, because A stands for amplitude. S, I gotta fix it here again. Power divided by surface area, S, cancels the S that we have, 2 pi squared rho V And I put that stuff in square brackets because that's really the important piece, that the intensity of this wave that's propagating through the medium depends on the frequency and it depends on the amplitude. Now, the amplitude part makes sense. So that's been there the whole time. The more energy we're putting in, because the bigger the amplitude of our disturbance, the more energy we get to propagate, the more intense that propagation looks further down the line, further down the medium. This dependence on frequency is maybe a little hard to see at this point. I'm going to use an app to make a tone, and we'll see if this comes across the video. This might make a little more sense next week when we talk about sound, but for now, okay. So I've got this tone generating app, and what I'm going to do is change the volume, and we should here perceive in the space from the source to the receiver, we're spreading that sound over a larger surface. So we should be perceiving some intensity that is different as we change the volume. And so I'm asking you, does it sound louder? If I turn up the thing? And I think yes, that the amplitude of the source obviously matters. That the louder the thing is, the more we perceive it. Okay, so what about this frequency bit? As far as sound goes, frequency we hear as pitch. Is a higher frequency sound is a higher pitched sound. So here's that same sound, and I'm not going to change the volume setting anymore. I'm going to change the frequency. I bet that this is coming through louder on your end than this. That this sounds quieter than this, even though the amplitude of the source is the same. As we decrease the frequency, the disturbance is harder to perceive, is less intense, that the volume we perceive isn't as high. And it's because of this, because of that frequency proportionality. As we increase the frequency, the intensity increases. Okay, let me go back to the slides. See, and again, there's that f squared a squared that we wrote here on the board a second ago. Okay. It says you can see, because I'm sharing my screen, that we're talking at 17 of 32. So we're about it. It looks like we're only halfway done, but it's going to go quick, I promise. A wave that's propagating can hit a barrier or an obstacle and reflect. So in this case, this pulse is coming to the right, and it's going to hit this end that is fixed. An obstacle like this that wave, that energy that we're trying to send, will get bounced back at us, and we'll get a reflection, an inverted reflection, that the instead of a crest will become a trough will be coming back towards us. On the other hand, a wave that reaches the end of its medium, a string that just gets to the end, or um, an obstacle, but an obstacle that we can still get through, that reflection won't invert. So we're talking about behavior of a fixed end and behavior of a free end. A fixed end reflection, we get an inversion. A free end reflection, we don't. We just get a reflection. Well, propagating from a light section to a heavy section of a string is like kind of hitting a wall. So we do get some of the energy to go through that sort of barrier, through that transition from one type of the medium to another. We also get some reflection because it's kind of like we hit something. We hit a heavier section than we were traveling in. That's an obstacle, right? So we get a reflection, and we do get that inversion, kind of like a fixed end. If we had the propagation reversed, if we were traveling in the heavy section towards the light section, we would get transmission, and we would still get reflection, but it wouldn't invert. We would get reflection of the just of the same crest we had. The pulse would just reflect instead of being inverted to the other side of the string. Okay. Instead of a one-dimensional string, let's talk about motion, wave propagation through an area, like, we were just talking about. So we can track the sort of propagation of the wave by tracking crests, places where all of these points in the medium have a crest, have a point of maximum positive amplitude. If we let some time go by, then that crest propagates outward, and then there's another crest. So there's another point in the medium where all of these points have the same crest, which is a crest later than the one we had a minute ago. Those are, well, we can call them wave fronts. Points where all collections where all of the points have the same crest. This crest, not the crest before it or the crest after. All these points are experiencing the same crest. If we will move very, 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 very far away from the source so that it doesn't even, so that we're looking at so small a section of spherical propagation, just just the tips of my fingers, so that they don't really look curved anymore, but they just look like flat sections of a wave. We can call those plane waves, like this. Okay. Plane waves can reflect just as well as waves along a string. The incident ray, remember that rays are the way we track the direction of propagation. We've got these incident wave fronts coming towards that boundary, and we've got the incident ray showing us that direction. The reflected ray bounces back, and the law of reflection says that those two angles are equal. That's like reflection. So in two dimensions, though, in more than one dimension, what does this like transmission, across a boundary type from a light section to a heavy section, what does that look like in two dimensions? And the answer is the same answer to the question, why does a pencil look bent in water? Because the wave travels differently fast depending on the density, depending on the character of the medium. The wave fronts are spaced closer together once we propagate into the water, for example. Since the wave fronts are closer together, but we need the wave fronts to line up from one side to the other, the only way to do that is to make these waves bent relative to the original ones. That's the only way to preserve both crest meets crest at the boundary, and also show that the spacing between the wave fronts, between, corresponding crests, has decreased, is to bend the direction of propagation. It's the only way to do that. These angles are related according to Snell's law. It's this. We can prove Snell's law if we want to with a little bit of geometry and a little bit of elbow grease. We don't need to at this point. Since we're talking about waves and how they behave, there's a couple other things that we should mention. One of them is diffraction, and that's the diffraction is the reason that you can still hear me, even though I'm talking directly into the laptop. There's really no good way for the sound to propagate through the laptop, not like it can propagate through the air, but that's okay because that disturbance will actually bend around the obstacle and fill in the space behind it. There's a shadow region, but eventually we can bend around and sort of recombine once we get past that obstacle. There are a couple other things that we can talk about waves doing, but we'll fill in those blanks on next week when we talk about sound, because they're a little bit easier to see when we talk about sound. What if we have two pulses approaching one another on the same string? An up pulse and a down pulse, when they get to the same point in the string, will precisely overlap, at least just for an instant, and we've got two sets of instruction. One says up, one goes down, so we average them out and we get nothing. And then an instant later, those two disturbances, they're still there. The energy hasn't gone anywhere. It's just the information, that the amplitude of one, the displacement of one of them has canceled the displacement of the other one. They have superimposed one on top of the other. We add them up, we get zero. The energy is still there, so those pulses keep going in their original directions after that instant when they overlap and yield nothing. What if they are both up pulses? Then we say one of them says go up, the other one says go up, so we go up twice. We end up with more amplitude than we had. So we can say that we've built something, we've constructed something. We can talk about constructive interference. They've, interfered with each other, interacted with each other constructively to build a thing, or in the case of figure A here, destructively to reduce the amplitude of the combination. Another way to look at it, if we've got one wave instead of pulses, if we've got a wave that's trying to propagate with another wave, if they add constructively, if they add destructively, and this is one case where they are adding kind of both. It's partially destructively, partially constructively. Sometimes they build something, sometimes they reduce the amplitude. Like, for example, here, there's a crest. So we've built something kind of, But here, there's a minimum. So whatever there was, we've destroyed. We've gotten back to, back to zero. With the, down from this one and the up from this one, we've averaged out to zero. Then later we build some negative amplitude, and then there's another zero where we destroyed some stuff. This idea of superposition, and the superposition specifically that occurs when one wave tries to add with another wave, that's going to be a piece that we talk about in chapter 12. There's an application to this. Oh, goodness, excuse me. Excuse me. There's an application to this interference superposition that we'll use to look again at that phenomenon of resonance that we looked at a little bit ago. Okay, the rest of the slides are just a summary of chapter 11. So I'll post these slides, and then and we're good to go. Cool. Thanks, everybody.